Hi everyone, welcome to the September ATAR Notes lecture series. I'm Isabel and today we will be going through HSC chemistry. Hopefully you do that subject or else you are watching this for no reason. But let's get started. If you want more resources on chemistry, um, you can go to the website. There's lots of stuff on there, lots of free resources. So go check those out because maybe this lecture isn't enough for you and you need more, but hopefully I can teach you a lot today, so that won't be a problem. But we're doing a revision thing today. We're going to go through as much as possible on HSC chemistry, so you'll feel super prepared for the HSC, which is starting to come up pretty soon. So yeah, I'm Isabel, and a little bit about me. I graduated last year, so 2022, and I currently study at the University of Sydney doing a Bachelor of Applied Science, Exercise Physiology. My subjects in high school were 3 unit maths, English advanced, chemistry, bio, and modern history. I got a band 6 in all of them, and my ATAR was 99.3. And now I'm a tutor here at TuteSmart, ATAR Notes, whatever. And yeah, so that's what I did. That's what I'm doing. Fun fact, I almost dropped chemistry in year 12. It was not my favorite subject, but once I got into the hang of studying for it and figuring out what worked best for me, I ended up getting pretty good in chemistry, which is nice. And some non-academic facts about me are like to dance and like to play touch and going to the beach and water sports. So if you look at the little pictures on the side, the top one is of me paddleboarding in Hamilton Island, which I did over the summer after the HSC. That was something to look forward to after my exams, was going on a holiday. And then the bottom one, which my face is kind of covering, but it's a photo of the quad at UCID, which is the big Hogwarts looking building in the middle of the campus. And I just think it's a really cool building. And I usually pass it on the walk from the bus stop to the building I'm usually at, which is SUAC. And when I see the building and it's got a nice blue sky in the background, it looks really nice. So I take a photo of it. So that's just one of those. It's a bit sad that my face is kind of covering that corner, but that's okay. That's a little bit about me. And now a little bit about what we're doing today. So the game plan is what we'll do is a rundown of all the modules. I tried to focus on some of the harder stuff and some of the more skills-based things because theory is something that, to be honest, most of it is not memorization, but it's learning the content, whereas skills is you have to practice applying it to a question. So I focus more on that, but we'll look at the that trickier is spelt wrong. I spelled trickier wrong there, but trickier aspects of each module. And we'll be doing lots of practice questions along the way. So if you want to follow along with the practice questions and try and get the answers before I put them up, then have like a pen and paper and a calculator and your data sheet with you, and you can try them for yourself. If you have any questions along the way, put them in the live chat, which should be happening besides this video right now. No question's a silly question because chemistry is hard. Understand that. So put whatever questions you want there and someone else will be answering them because usually I would be answering them, but I'm at uni games when you guys are watching this, so I will not be there to answer the questions. But I'm sure whoever is answering the questions on the live chat will give really good answers and that will be fine. So just put anything you want in there, any questions, not anything random, any questions you have there, and then they will be answered as quickly as possible. But before we get into the revision content stuff, oops, why is that not, why is that not working? There we go. Something to remember is that the HSC is never worth compromising your health. So it's normal to feel stressed, that's fine, but you don't want to cut yourself off from everyone and only study. You don't want to cope with stress in an unhealthy way because it's just not fun. It's going to make the worst month ever during the HSC. So make time for friends. Even things like having study dates with your friends, like going to the library all together at the same time. Even if you're not a group studier, you could go to like a quiet room while everyone else is like in the main area to get your actual study done, but also still make time to speak to your friends. So like make sure that you are coping in healthy ways. And also catch up on your sleep. It's natural to feel like you're running out of time and trying to get back that time by not sleeping, but that is not a good idea at all. It is bad for your health, firstly, and also like your brain is not going to like you for that. And it, especially if you're doing it the night before an exam, usually it ends up with worse results than if you got a good night's sleep. So try catch up on sleep during the HSC. But overall, just believe in yourself and trust your preparation because if you think about it, you're not going into the exam having done nothing. You've done a whole year's worth of practice questions and going to classes and all of that. So you are prepared to an extent. So you got it. It's all good. But if you're still feeling a little bit like shaky about the HSC and stressed about it, that's what these lectures are for. So use this time to ask questions to people who have done the HSC for chemistry before and use this time to like revise and actually try the practice questions that will come up on your screen. Like don't waste an opportunity to improve. That's what I'm saying. But yeah, cool. So first thing that I will go through is a little bit of general exam technique. So everyone approaches their exam differently. It's a 3-hour exam. It's quite long. Usually people finish with a lot of time left, and that means time to check answers. So don't leave your exam early. I know that you can technically leave early if you've finished, but I would advise against that just because you might go through your paper and find something that you did completely wrong the first time, and then you have those extra minutes to make it up. But in general, for timing, multiple choice generally takes 40 minutes, but it can take more because, as you probably figured out in your trial, chemistry multiple choice is evil. It gives you a question that is worth probably 6 marks if you had to like do it with full working out. And it's only worth 1 mark because it's multiple choice and it can be really hard sometimes. So it usually takes about 40 minutes for those 20 questions, but it can take up to an hour. So don't don't try to go over an hour with multiple choice because there's always going to be more questions to do. If you're really struggling, multiple choice is 1 mark per question, whereas the rest of the paper usually has a lot more marks allocated to it. So you're safer to, after 40 minutes to an hour, to leave the questions in multiple choice that you were struggling on and then coming back to them later if you have time rather than just getting multiple choice done and then not having enough time for the questions that have bigger marks towards them, if that makes sense. And that's the other thing, like check how many marks each question is worth. It's an indication of how much time you should spend on the question and also how you should structure a question. So if a question is only 1 mark long, like multiple choice or like a quick identify this reaction, you don't want to be spending too much time on it. It should be a really quick answer. And for the longer responses, if it has, let's say, 7 marks to it, that's usually for one of your module 8 like spec questions, organic analysis questions. Usually those are around 7 to 8 marks. When you get one of those questions, that's about like 2 marks worth of like yeah, 2 marks for every graph that you have to analyze to get your final answer. So just write that amount, just use it as a guideline for how much you should be writing for everything and how many points you should be hitting in your answer. Another thing with exams is that in the HSC, there's one question in every paper that has a mark allocated for getting the right amount of significant figures. So what that means is the least amount of significant figures in the question. So let's say it's 4 significant figures, that's what your answer has to have. Your answer has to have 4 significant figures. And that's just an extra mark. So you don't know which question in the HSC has that extra mark allocated for significant figures. So it's always a good idea to get into a good habit of always putting the right significant figures just in case the question is that question. And then another thing is to consider your ordering. Everyone goes through the exam in different ways. Some people like to do short answer first because it's worth more marks and then go on to the multiple choice. Some people start with like looking through the paper during the reading time and then they look at the questions they know the answer to immediately, get those out of the way, and then go to the weaker sections after and spend more time on those. And other people just follow the paper order. So whatever works best for you, it works for different people in different ways. For me, I just followed the order of the paper. I did one round through. If I didn't know how to do a question, I'd skip it, and then I'd come back to those trickier questions when I had extra time, and I usually had a lot of extra time, so I'd always finish my paper. But you can go through your paper however you want. Just make sure that you don't try to like change up the way you order your paper midway through your exam because then you might get confused and you might end up wasting time. So just stick to one way of going through the paper and stick to that the entire 3 hours. And then, yeah, back to my original point, but always leave time to check your work. Don't think that because you finish your paper, you're done. No, you should always go through a second time, going through every single question again, just to make sure that you've gotten as much right as possible and you've maximized the amount of marks. So that's just a little side on exam technique. Oh, not again. And now for study techniques. So for me, chemistry was all active recall basically. For calculation-based questions and skills-based questions, I just did a ton of practice questions that my school gave me and also that I found online from other schools' past papers and past HSC questions. My HSC, the 2022 one, has a lot of good calculation questions in there. Um, so use the 2022 HSC past paper. Some of them were really tricky. So not tricky, but like a little bit, they stumped me a bit at the beginning. But yeah, definitely do a bunch of HSC practice questions. Another thing you can do are flashcards. And flashcards, like you know what flashcards are. Um, but what you have to do is just go through your flashcards for the theory-based stuff rather than the equations. Also for like the different types of reactions that I use flashcards for in module 7. But flashcards just help me remember things better. And since I had to like actively recall it, since it was an active recall exercise, it was much more useful in training that part of my brain to be able to like spit out that information during the actual HSC. And same thing with blurting. Usually I did flashcards and blurting hand in hand. So blurting is just when you get a blank piece of paper and write everything you know on a topic. And I did this for like my different reactions. I did this for my different theories on acid and bases. So the four dudes plus Bronsted-Lowry. Um, then I also did it for things like fuel choices and different type of esters in, not esters, polymers. I was thinking of polyester, but the different type of polymers in module 7, I just blurted that and it just helped me remember everything and check that I could get everything out and actually write everything down in an exam kind of situation. And then what I would do afterwards is I'd get a pen that was a different color or a highlighter and I would write what I missed out from my notes in a different color so it stood out, and then I'd be able to remember it easier next time I did flashcards or blurting. And another thing to do is quiz your friends. So if you have a friend that does chemistry as well, you can just quiz each other, and that's usually really helpful because if you can teach someone else something, and if you can like answer and ask them questions and like exchange ideas like that, it's it's useful. But yeah, and the main aim of study, something you should remember, is that you want to eliminate your weaknesses and limit your silly mistakes. So you don't want to just be doing practice questions for the stuff you're strong at because it makes you feel better. I know I did that sometimes. I would do a lot of titration questions because that's just something that I found much easier than module 5, and I would do tons of those, and it made me feel like I understood chemistry a lot more. So since it made me feel good, I just focused on that. But then I became really weak in my module 5. So then I had to work even harder to get my module 5 back up to par with everything else. So don't ignore your weaknesses and focus on your strengths, but at the same time, don't like leave your strengths and never practice them. Just try to balance it out a little bit and work on making sure that every topic is even and you have a good amount of skill for everything. Um, so yeah, that's that. Um, Now we go into module 5. So module 5 is equilibrium, and equilibrium is one of the trickiest, I'd say. I think that it's the trickiest module, but that might just be me. And yeah, so basically equilibrium, oh sorry, if I look onto this side, that's because this is where the monitor is. So if I'm looking over here, I'm not ignoring you, I'm just looking to where the text is bigger. So yeah. Module 5, Le Chatelier's principle is the big part of Module 5, and it's that when a system is at equilibrium and it is disturbed, it will reestablish a new equilibrium to minimize the initial change. So we're not amplifying the initial change, we are bringing it back to how it was originally to minimize the initial change. So basically, it tries to reduce the amount of change by acting in a certain way. And this is how equilibrium works. And if you think about it too hard, you might get a little confused. So just try to think of it in this very simple Le Chatelier way where it's just um, it change happens, and then when the equilibrium is being reestablished, it tries to minimize the change. Um, but if we look at this example here, we see that there is a reaction, nitrogen dioxide, and then nitrogen tetroxide. Hopefully I said that correctly, but this is exothermic reaction. You can tell because delta H is negative, and that's basically all we need to know. So you see the ratio 2 on one side, 1 on the other side, and we have an exothermic reaction. That's what we need to know to start with, to start looking at how it changes when we change the equilibrium stuff. So if we look at increased temperature, so temperature, if you remember from your like KQ stuff, we'll go through it again in a couple of slides, but temperature is the only thing that can change your equilibrium constant, but we're not talking about equilibrium constants yet, so like don't worry about that too much. But basically, if we increase the temperature, we want to reduce the amount of heat, right? Increase the temperature, minimize the change by reducing the amount of heat. So we want to favor the side that absorbs heat. So we're not going to go to the right, which is exothermic. If we're going the forward reaction, we are producing heat. We don't want that. We want to absorb heat. So we are favoring the reverse reaction, which takes in the heat. So that's increased temperature. If you decrease the temperature, the opposite will happen. So if you decrease the temperature, it doesn't like it anymore. It wants to get warmer. If it wants to be warmer, it will have to produce heat, and producing heat is an exothermic reaction, and the forward reaction is exothermic. So it will favor the forward reaction. It'll shift right. That's how it works. That makes sense? And then for pressure. So pressure is just like concentration, but for gases. And basically we have one side that produces 2 moles and one that has 1 mole. So if you are increasing pressure, this is usually a result of a decrease in volume, but an increase in pressure means that it doesn't it's colliding more. It doesn't have as much space. So you want to have less amount of gaseous particles to counteract that change. So you want to go to the reaction that produces less molecules. So how I think about it is when you are increasing pressure, you're usually decreasing the volume, which means there's less space for the particles. And when there's less space, you don't want lots of stuff in there. You want the smallest amount as possible so it's comfortable in the least amount of space. So that's why you go to the side that has less moles of gas because it'll be more comfortable. That's just how my brain thinks of it. I'm sorry if that was explained kind of poorly. That's just the way my brain thinks of it. But basically, it goes to the side with the less number of gaseous particles. So on this reaction, it'll go to the right because the right has one and the left has two. So it'd go to the one with less, which is the right. It will favor the forward reaction. That's that. And same thing with decreased pressure. It has more room, um, usually because it's an increase in volume, and this means that it will have less collisions happening, and you want to increase the number of collisions. How you do this is add more particles, and how to add more particles, you favor the side that has more gaseous particles, and that would be the left side here. So your reaction will shift left, and it will favor the reverse reaction. Hopefully that makes sense. Um, Same thing with increased concentration and decreased concentration. If you increase the concentration of one thing, so in this one it's nitrogen dioxide, if you increase it, you want to get rid of it basically. So you use it up more and you use it up making the forward reaction. So that's why it shifts to the right. Since it's more of it, it's being used up more, shifts right. That's how it works. Same thing with if you increase the other side, one reactant's increasing, it wants to be removed from the system because it wants to counteract that change of the increase. So you're using it up in the reverse reaction. Therefore, shifts left, favors the reverse reaction. So in the kind of opposite side, if we have a decrease in N2O4, what would happen is that increase, it's the same as a relative increase in nitrogen dioxide. So like what we saw in the last slide where it favored the right and the forward reaction, same thing would happen if you decrease N2O4. It would favor the forward reaction because that decrease, it wants to counteract that. How to counteract a decrease in something is to increase it up again by making more of it. That's why it favors the forward reaction. Hopefully this is making sense, but we will try it out in a little bit of a practice question here. So this is what happens when the volume of the container is halved. So this is something to do with pressure. If we look at the reaction, first thing to note is how many moles of gaseous particles are on each side. So on the left-hand side, we have two. So two there, and then on the right-hand side, we have one. So two on one side and one on the other. When the volume of the container is halved, decrease in volume, since volume and pressure have an inverse relationship, that means we have an increase in pressure. When the pressure is increased, what happens according to Le Chatelier's principle? What happens is that we want to favor the side that has the least amount of gaseous moles. So we would shift to the right. We would shift to the right so that there's less moles. That's how it works. So the answer for this would be C. Hopefully that makes sense. We'll do another one, which is this, which has a little bit more writing and a little bit more critical thinking. But basically, nitrogen dioxide is brown, dinitrogen tetroxide is colorless. So on the left we have brown, and on the right-hand side of the equation we have a colorless gas. Then what happens is that at room temperature it is light brown, at higher temperatures it's a deeper brown. So what happens is as temperature increases, it becomes a deeper brown, which means as temperature increases, it is shifting towards the left because we know that nitrogen dioxide is brown. So increased temperature means a shift left. Now we have to work a little bit backwards on this, but if there is an increase in temperature and it is shifting left, that means that the shift left, the reverse reaction, is endothermic. And that is our answer. The reverse reaction is endothermic. It's A. If we look at the other options, B, the forward reaction is endothermic, that can't be right because if the forward reaction was endothermic, then what would happen is if there was a decrease in temperature, then it would become more brown. But that's incorrect. So it's not B. C, brown color is due to strong nitrogen oxygen bonds. That's not what the question's about. It's about equilibrium, so you can ignore that one. And D, equilibrium concentration is not dependent on temperature. That's also incorrect. So that's just not an option. So A has to be correct. So when you get a multiple choice question and like the first answer is you think it's correct, always just go through the rest just in case, because sometimes there are instances in multiple choice where there are multiple correct answers in the multiple choice, but you're looking for the most correct answer. And while that's a little bit trippy sometimes and it's getting a little bit confusing on what's most correct, just look through all of the options because it will make itself clear the more that you read the options. So yeah, that's that. Another type of question you could get for Module 5 is this, which is one of these diagrams. And basically we have the Haber process here, and it's an exothermic reaction, and it shows us the changes in concentrations at different time points where disturbances have been made at equilibrium. So if we look at T1, we see a spike in the N2 line. So that means that at T1, there was an increase in the concentration of nitrogen only. Nitrogen only was affected, so it's an increase in nitrogen concentration. Then, if we look at T2, you can see that it shoots up for all of them. There's a line going up for all of them. And what that means is that there's been an increase in concentration for all the species in the vessel. And since there was an increase in all of them, that means that there must have been an increase in pressure. That's how it works. Then if we look at T3, it is a soft little curve for all of them. So my general rule when looking at this is if it's a spike for all of them, it's a pressure change. If it's a curve for all of them, it's a temperature change. So we're looking for a temperature change here. If we look at what is going up and what is going down in concentration, we can see that the ammonia is decreasing. The other two are increasing, the ammonia is decreasing. So what that means is that it is favoring the reverse reaction. Favoring the reverse reaction. So it is an exothermic reaction forward, endothermic reverse reaction, and at T3, something has happened for it to favor the reverse reaction. So the temperature change must have been an increase in temperature. That increase in temperature will cause it to favor the reaction that absorbs heat, which is the endothermic reaction, and that's the reverse reaction, which is why it's a decrease in ammonia. That makes sense? If it doesn't, put a question and someone will answer it. But now onto the tricky numerical stuff. We have the equilibrium constant. So equilibrium constant, KEQ, it tells us the concentrations that are present at equilibrium. So it's a little bit of an expression, I guess. And what happens is you put products on the top and then you put your reactants at the bottom. And what you need to do is your twos that are at the front, those become squares. If it was a 3, it'll become a cubed of the concentration. So you move it up to become a power of. And basically, you can plug in numbers here to get an actual number expression of the KEQ. But for all questions where it requires the equilibrium constant, you should always have a line of working where it looks like this with just the like elements and concentrations, not any numbers yet. So that's what the equilibrium concentration is. There's a few special ones. There's Ka, which is acids, and this is just the acid version of KQ. It only applies to weak acids because weak acids are the only ones that are in equilibrium. Strong acids are dissociating completely, so we don't have that equilibrium. And you'll see in the acid ionization equation that there is a water that is not included, and that's because water doesn't have variable concentration. It should have a liquid state. There it's aqueous, but it should be liquid state. And yeah, so you ignore that. That's why the bottom is the concentration of the acid only, and then the top has the hydronium and the conjugate base concentration. And it's very useful because when you have weak acids, you might not be able to calculate the pH without considering Ka because Ka can help you find out the hydronium concentration. So this is a really good thing to remember when it comes to the HSC because they really like having those hybrid questions of multiple modules, and Ka is a really good way for them to cross between Module 5 and Module 6. So keep that in mind for the HSC. But there's also KSP, which is solubility product. So on your data sheet, you have a bunch of KSPs on there, and this it's really useful because KSP has a lot of question types that you can get, but it's used for finding stuff to do with dissolution and the solubility of substances. And it's basically a product because if it starts as a solid and then it's dissolving, we can't have a solid in our equilibrium expression. So a solid doesn't have a concentration, its concentration is like 1. So it'll be everything over 1, and that's just a product between the two ions. So that's why it's called the solubility product, and that's why it looks like that. So for the example at the bottom there, you have 2 sodiums and then 1 carbonate. So your expression would be your sodium concentration squared multiplied by your carbonate concentration. And then you completely ignore the solid basically. So some practice questions. This is an example of those pKa, Ka questions. So pKa is something that isn't talked about a lot, but it's really similar to pH in that pH is minus log hydrogen concentration. And it's basically the same for pKa and Ka, that relationship. So if your acetic acid pKa is 4.8, then your Ka is 10 to the negative 4.8, just like how you convert between pH and hydrogen concentration or hydronium concentration. So if we have that Ka that we find out from doing that calculation, 10 to the negative 4.8, then we can find out the pH of the 0.5 solution of acetic acid. How we do that is we use the Ka. So we write out an equation of how acetic acid like reacts with water, and we'll find that our Ka expression is the concentration of acetic acid at the bottom, and then these two mystery concentrations on top. Then you do the maths of it. So basically, it's an ice table. So a good rule of thumb for Module 5 is that if you are doing equilibrium calculations, you should always write out an ice table. If the ice table ends up being redundant and you actually don't need it, you have all the information you need without working anything out from the ice table, then you are all safe. That's fine. You can just ignore the work you did on the ice table and move on. But if you start something that actually requires an ice table and you haven't done it, you'll get a really different answer. So it's always just a safe bet to try an ice table. And if it doesn't work out, it doesn't work out. But if you do end up needing it, that's great. You can use it. It's just much safer to always just try writing down an ice table so you can kind of visualize what's happening. But we wrote that equation up. Then the next thing to do is to make that ice table. So we start off with 0.5 of the acid. And then technically, a little bit disappears when establishing equilibrium. That's why it's 0.5 minus x, which is that little mystery concentration going on there. So the x ends up being super small, so we can say that it's negligible and then just assume that it's 0.5 on the bottom. And then the next thing to note is the x. So when you're dissociating an acid, you will always have the same amount of hydronium and the same amount of the conjugate base because you can't get a hydronium without getting a conjugate base, if that makes sense. So that's why they're both x. They're not two different variables, they're both x because they have to be in the same amount because that's just how it works. So that's why we can make it up to be x squared over 0.5 is equal to the Ka that we calculated as 10 to the minus 4.8, which ends up being 1.58 times 10 to the negative 5. And then you do your little algebra, move it over to the other side, then square root it, and you get x having a concentration of 0.0028 moles. Now that's all good and that's all well, but you're asked to find the pH. So that X is the concentration of the hydronium. So we can use it in our pH calculation formula to find the pH. So minus log of 0.0028 moles, and then we get 2.6 to 1 decimal place. And that's how you do it. So it was a combination of your module 6 calculations of pH and your module 5 ice table equilibrium stuff. So the main places you can go wrong in a question like this is first of all the ice table. If you don't do the ice table, you can get very confused, but that's fine. Once you have the ice table down, it's actually quite easy from there. Another place people go wrong, or not go wrong, but go a very hard way, is they don't make X negligible and they don't make that assumption. So they do quadratic equations. Try to avoid that. Just most of the time, X can be negligible, so you can ignore that and move on. But yeah, a lot of the rest is just simple algebra, so it should be fine, but it's setting up the ice table first that can get a bit tricky. Next thing is a KSP question, which I think are the hardest ones. But if the KSP is 3 times 10 to the negative 34, what is its solubility in grams per liter in water? So how you would go about this is first write out the dissociation equation of aluminium hydroxide. Once you write that out, write out an expression for KSP. So that'll be the concentration of aluminium cubed, so to the 3, and then the concentration of hydroxide, it's a product of those two. Then what you need to do is make algebra out of it. So I will show you what I mean. There's an ice table. The ice table isn't necessary in this case, I would say, mostly because you can kind of logic it out based on the equation you write out. Sorry, I think before I said that there were 3 aluminiums. No, it's 3 hydroxides. I don't know why I said 3 aluminiums. But anyway, once you've written out that first equation on the dissociation of the solid, then you can kind of figure out that 3x is OH, and then you can sub it in like that. The ice table isn't really necessary. You can kind of skip the ice table step if you're comfortable, but if you're not comfortable, then the ice table is a really good idea. But yeah, your OH, since there's 3 amounts of change happening, it's 3x, whereas for aluminium, it's just x, and then you sub it in. So overall, your KSP is 27x to the power of 4. Then what happens is you make that 3 times 10 to the negative 34 equal to that 27x to the power of 4. Then divide by 27, and then you root it in 4, and then you find x. And then x will be the molar solubility of aluminium hydroxide, but we're trying to find the solubility in grams per liter. So then what you need to do is you need to multiply the molar solubility by the molar mass of aluminium hydroxide, and that'll give you the solubility in grams per liter instead of moles per liter. So the main places that can go wrong here are, first of all, forgetting the 3x. I just remembered, like, you just kind of, once you do more practice questions, it's kind of natural to put in the 3x or the 2x or however many x's. But some people just forget about that completely and think that the cubing is enough. It's not enough. You got to put that 3 in there or that 2 in there or whatever number you're putting in front. It has to go both in the brackets and also above the brackets. Then another place where it goes wrong is not checking the units they want it in. So it says find the solubility in grams per liter. You want it in grams per liter. You don't want it in moles per liter. So when you get X, it's in moles per liter. You don't want that. You want it in grams per liter. So you need to make that conversion using the molar mass. That's something that people forget, and that's something that can be very easily fixed. It's just 1 mark gone if you forget to do that. So it's something very fixable and something you should definitely try and remember. So always read the question. I liked to underline the units in the question or underline like the key parts of the question, especially in these trickier ones. So I'd remember, but to each their own in terms of how they go about like marking their paper. So just remember to make those conversions in units if necessary. It doesn't just apply to Module 5, to a whole ton of different modules and types of questions. Units are very important. So we'll do this practice question, which is determine what mass of magnesium carbonate could be dissolved in this solution. So it's magnesium carbonate being dissolved in sodium carbonate. This is the common ion effect. What we need to do here is an ice table. So in this case, our initial concentration is different. Our initial concentration starts at 0.001 because that's the concentration of sodium carbonate, and that'll be the concentration of carbonate in there. Then what you do is you treat it as a normal KSP equation where it's x, and then x is considered negligible for the 0.001 plus x. Then since it will be such a small change, then you use that product to figure out the x, because KSP of magnesium carbonate will be on your data sheet. So once you do the maths to figure out x will give you the solubility of magnesium carbonate in moles per liter. Once you have that, what you need to do is you need to figure out the solubility in grams per liter. Once you figure it out in grams per liter, which you do by timesing by the molar mass of magnesium carbonate, you will get a number of grams per liter that can be dissolved. And that's your answer. You have to word it as like in 1 liter of this solution, this amount will be dissolved. You need to specify that it's a solubility in 1 liter. It's the mass in 1 liter, if that makes sense. You don't want to just say 0.58 grams can be dissolved, because it doesn't say in the question how much, like what the volume of that solution of sodium carbonate is. So you need to specify in your answer to make sure that your answer is correct. But yeah, basically what you should be getting away from all these Module 5 questions is that ice tables are important and they save you from making mistakes. So for all those practice questions we just did, they're all ice table questions, and that's good. You should be doing all ice table questions basically, because all equilibrium can basically be put in an ice table question. So try to get used to them and try to get good at filling them out properly. So for example, in this one, we start off with a different initial concentration, not both starting off as 0, which is how it usually is in a dissolving kind of question. So being careful with those kinds of things can make a really big difference in Module 5. These are some other practice questions. I won't go through them in detail, But these are just here so that when you get like the copy of the slides or like the recording of this lecture, you can go back and do these questions as practice for your HSC. Won't go through them now, but yeah, just go through them in your own time once you get the slides. They're good questions to practice, just writing and calculating. So yeah, we'll move on to Module 6. Module 6 is titration acid-base stuff. A lot of the start is theory, and theory is just something you have to remember on your own, but the skills is something that we can go through a little bit more today. First thing is acid-base models. So we have these four ones that are kind of mandated for us to remember, and that's Lavoisier. He thought that if there was oxygen in a compound, it had acidic properties. So if it was an oxygen with a non-metal, it had acidic properties. It was very limited because like hydrogen, not hydrogen chloride, hydrochloric acid is obviously acidic and that has no oxygen in sight. So it didn't explain why those were acidic, and it also didn't explain why some metal oxides were alkaline instead of acidic. So that was a bit of a bust, but Davy, who is the second one, they thought that the electrolysis of HCl, um, it showed that there was no oxygen, which like got rid of the original theory, and they said that have um, it must have hydrogen in it, not oxygen. Must have hydrogen in it, which is sort of true, but like a lot of acids have hydrogen, but it's not what makes it acidic. And they also thought that bases react with acids to form salts, which is also true. But the limitation of this is that some hydrogen-containing compounds aren't acidic. So, like, what's going on there? If acids are things that have hydrogen, why are hydrogen-containing compounds not acidic? So that was a question there. Arrhenius was the next one, and this one is a little bit more advanced, this theory. A big step away from the first two, but he proposed that it's due to the behavior in water, which determines whether it's an acid or an alkaline, and said that acids dissociate to form H plus ions and bases dissociate to form OH ions, hydroxide ions, and that neutralization involves the product of a salt and water. Um, and this is all true, but the limitations of this is that it only worked in aqueous substances. So sometimes, like acid-base reactions can work in like a gaseous situation. So the reaction and behavior in water didn't explain that. And also, it did not explain why some salts had a pH, some had acidic and basic properties. So it didn't explain that, which is where we get to Bronsted-Lowry, which is the most full theory, I guess. And it's just that an acid is any chemical substance where a proton can be removed. It included gases now, so it's not just in aqueous solution. It includes gases, and acids are proton donors. Then base, any chemical substance capable of accepting a proton acceptors. It can also be a gas. So proton means hydrogen ion here, and like side part of the theory is that an acid can only donate a proton if there is a base to accept it. So this also explains the interactions with water, because water would act as a base for acids. It can be an acceptor of that proton. Yeah, so those are the theories. There's not too much to remember with these, but just know them, know their main finding, and know their limitation. But for Bronsted-Lowry theory, um, this is the main one we use, and it's just that proton donors are acids, proton acceptors are bases. And this is how it works. If you look at the differences between a weak acid and a strong acid, you'll see that weak acids exist in equilibrium, strong acids ionize completely. That's why it's a complete arrow. Um, So this way, we have like differences between proton donors and acceptors, and um, Arrhenius' theory was talking about how weak acids and strong acids are differentiated by their degree of ionization. So that was correct, and that's still applicable in Bronsted-Lowry. But same thing with strong acid, weak base and strong base are the same thing. Weak bases exist in equilibrium, strong bases dissociate completely. And then we have neutralization reactions, which are reactions between an acid and a base. And what happens is that it forms water and a salt. And because basically the net reaction is the same, the net reaction boils down to hydrogen plus hydroxide equals water. They all have the same enthalpy, and that's negative 57.3. So that's the delta H for basically all acid and base reactions. And yeah, so neutralization is exothermic. A practice question for Module 6. The main calculations you'll get for this are your calculations of pH, which your formula is on the data sheet, I'm pretty sure, so it's not too hard. But the main sort of tricky one that you could get is a titration question. So titration, you should know the process for your HSC because it's a conduct part of your syllabus. It says conduct a practical investigation, so you have to know what to do to conduct a practical investigation. But the main thing that you have to do with titration is be able to do these calculations. And really, if you are good with your moles and if you are careful with your moles, titrations are easy. The calculations are much easier than your equilibrium calculations, in my opinion, because this is literally just like ratios and maths and being careful with those. So I don't really have like too big of an issue with these, but if they're not your thing, that is okay. That's why we're going through them today. So first thing to do, you look at what reaction is taking place. So it's always a neutralization reaction with titration, and this time it is hydrochloric acid and sodium hydroxide neutralizing. Then you look at what do we know. So we know that it takes this amount of sodium hydroxide to neutralize 25 mils of this concentration of hydrochloric acid, not hydrochloride, hydrochloric acid. So what can we get from that? Doing some easy calculations, we can figure out the number of moles of hydrochloric acid that was neutralized. And once we figure that out, we can use the 1-to-1 ratio, which we found in writing our equation. We can use a 1-to-1 ratio of hydrochloric acid and sodium hydroxide to figure out the concentration of NaOH. So how that works is we figured out the moles of hydrochloric acid, and we did that by multiplying the concentration by 0.025. Remember that concentration in moles is in moles per liter. So since it was in 25 milliliters, we have to convert that into liters before we can multiply it, which is why it's 0.025. Then we get the number of moles. Once we have the number of moles, we can use the 1-to-1 ratio to figure out the number of sodium hydroxide moles, and it'll be the same because it's a 1-to-1 ratio. Then the next thing to do is find a concentration. So C equals N on V. N is that 0.00249, and V is the 23.49 milliliters. Turn that into liters, so it's 0.02349. Then you find your concentration. For significant figures, there are 4 significant figures as like the smallest amount of significant figures in the question, and that's why the answer is in 4 significant figures. I don't know why it says 2 significant figures there, because it's obviously 4 significant figures. Just ignore that. The answer is in 4 significant figures, so that's what it should be in. There we go. That's that's how you do a titration question. The main steps in doing one of these is first write out the chemical reaction that's happening, then write out what you know. So we knew we had enough to figure out the moles of hydrochloric acid. So we did that. And then you have your mysterious, like your mystery number, which is your concentration, and you work towards finding it. So the main places where it can get a bit tricky is when that ratio is different. If it's not 1-to-1, you'll have to make some adjustments in your moles. So that's why it's important to write out that first chemical equation reaction so that you know the ratios and it's clear to you. So in a question like this has a different ratio. So we have acetic acid with magnesium hydroxide, and we can see straight away that because of magnesium hydroxide, it has that 2 outside of the hydroxide, which tells us that it's already going to be a 2-to-1 ratio, but still need to write it out. And then we know that 25.03 milliliters of magnesium hydroxide in that concentration is used to neutralize 25 mils of the acetic acid. So same process as before, just a different ratio. What we need to do is write out that chemical equation. Once we've written it out, we can figure out the moles of magnesium hydroxide by multiplying 0.1001, which is the concentration, by the 25 milliliters, 25.03 milliliters, just put in liter form, which is why it's 0.02503. Once you have that, you'll see it's a 1-to-2 ratio of magnesium hydroxide to acetic acid. So there was 1 magnesium hydroxide to 2 acetic acids, which means that we have to multiply by 2 to find out the moles of acetic acid being neutralized there. Once you find that out, you can divide it by your 0.025, which is the 20 mils, and that'll give you your concentration. This is also a 4 sig fig answer because the question has 4 sig figs for everything, so it should be 4 sig figs in your answer. Does that make sense? If it doesn't, leave a question and someone else will answer it. But hopefully this is making sense. Another thing that you need to be confident with is titration graphs. So there are lots of different types of titration graphs. Most of the time they look like a little curve like that. Like, where's the camera? Yeah, a little curve, like an S kind of shape. But this obviously does not look like an S, and that's because there is a different type of titration graph. This is one that is done with conductivity. You can see conductance is on the side. And what you need to do is be able to understand these as well. So not just understand the pH titration kind of graphs, but also the conductivity ones. So for this, what sort of titration will it be? This would be a strong acid, strong base titration. Strong acid, strong base. How can we tell that? Well, in general, strong acid, strong base, they have that very strong B shape. And what happens is if you were to justify why it was shaped like this, let's say you start with an acid, has high conductance because it is a strong acid, it's dissociated completely, lots of free hydrogen ions around, hydronium ions in the solution. Then once you're starting to add your base, more of those ions are reacting with the hydroxides from, let's say, like sodium hydroxide. The hydroxides are reacting with those hydrogens to form water, and that's no longer charged. It's no longer being picked up by the conductivity graph. So that's why it's going down. It's becoming less and less conductive because you have less and less ions free. Then, once you get to the neutralization point, all of the neutralization has happened. You have all waters possible made. Everything is done. Then why it goes back up is now you're adding, let's say it's sodium hydroxide. Now you're adding sodium hydroxide in excess. So that extra hydroxide that's coming in, there's no more H to neutralize it because you've already reached that point. So the more hydroxide that comes in, you're increasing the conductance because that's charged now, and it's not being neutralized anymore. So that's why it goes back up. So you just write something along those lines to explain the shape. So As it's being neutralized, it goes down, and then as it's being added in excess, it goes back up. But yeah, you need to be able to read these graphs and know what's going on. And that's what's going on in this graph. So that's that. Some other practice questions that you can do are finding like final pH of a solution. In this case, it's adding hydrogen chloride with sodium hydroxide. So some of it's been neutralized. How you would work this out is find out the moles of each after writing out a full reaction. Finding the moles of each, then finding out what would be in excess after the neutralization has occurred, and then you find the new concentration based on that. So what I mean by that, it's kind of hard to explain without me like drawing anywhere, and I don't know how to do that because I'm not that tech savvy. But basically what you need to do is you need to write the equation, find the moles of each, and then you'll see that there is more of the sodium hydroxide than there is hydrochloric acid. So since that's in excess, what you do is you find out how much in excess it is by minusing the 0.0875 from the number of sodium hydroxide moles, and that gives you 0.025 moles, which gives you the concentration of both sodium hydroxide, but also the concentration of the hydroxide ion itself. Then what you can do is find the pOH by minus logging it. Once you find the pOH, you can find pH by taking the pOH from 14. So pH is 14 minus pOH, and that's how you get 12.4. That's how you would go about a question like this. Same thing with all the other like titration, neutralization, acid base calculations is it really comes down to how careful you are with your moles and how well you understand the moles that are being tossed around in the question. So in this, you need to be aware that one will be in excess, and then that's that. But one thing to note is that the 0 point, actually, I have a bit of an issue with this. There's a bit of an issue with the slide. So one thing to note is that the number of moles, 0.025, that is the number of moles of, yeah, so that is a number of moles. You need to put it in concentration before you get to the final answer. So you need to put that over the new concentration of 0.5 liters because it's 350 mils plus 150 mils. So what you do is you put 0.025 over 0.5, and that'll give you 0.05. And once you've got 0.05, that's what you put in the negative log to find the pH. And then the answer should be 12.7 now. So I'll tell you the issue with this. I don't know why the answers were wrong. Sorry, I did steal this slide from someone else, so that's probably why. But the main thing to note, sorry for the mistake. Hopefully this will clear it up. But you can't put a number of moles into the pH like equation calculation. It needs to be a concentration, and that concentration you find with C equals N on V. Your N will be that 0.025, and your V will be the total volume of the solution now. So that'll be the 350 mils plus 150 mils, which is 500 mils, which is 0.5 liters. So that's a calculation you have to do before plugging it into the pOH equation. Sorry for the confusion there. Did not mean to confuse you guys, but hopefully that clears it up now. The answer is still very similar. It's just that extra step made a 0.3 difference in pH, but that 0.3 difference is a lot. So be careful with that. I'll fix the slides for when you guys get it properly in like as a PDF or something so that the answers are better there. But to be honest, I'm not in the mood to record this over again, so that's why I'm just explaining it now. Anyway, that is that. these are some more practice questions that you can do to practice your calculation skills and also your short answer writing skills. One thing I will point out is in the second question, it's a sample of stomach acid being analyzed to determine its hydrogen chloride concentration. This sample is taken, it is added to this solution, and then it's titrated again with sulfuric acid. It is a back titration question, and back titration questions can be a bit scary because there's two kind of steps, two titrations happening, but the way to approach them is to do them backwards. So you start with the titration that happened last, and then you work towards the initial one. Um, it's literally the exact same as a normal titration, except you do it twice and you need to be super aware of your moles and your ratios. But if you understand like what titration is and how reactions work, back titrations are no different from your normal titrations. So I won't go through that, but that's something you should definitely try practicing at home because back titrations are a really common HSC question. And I think that if you know how to do a titration question normally, where it's just one titration, you will be completely fine to do back titration questions because it's the exact same thing, exact same process. You just do it twice, basically, for the two different titrations. And you use your knowledge from the first titration to go to the second one. It's pretty simple. But what we'll do now is Module 7. So Module 7 is organic chemistry and it is fun. This is my favorite module, and that's because I think that it is easy, but whatever, it can be a bit hard, but the nomenclature is pretty chill. You don't get many questions on this, but it's still a skill that you have to be able to do, which is why we'll go through it quickly. So what you need to do is find the longest chain in the molecule. Sometimes the longest chain is a little bit hidden, so just count to make sure that you have the longest one. But in this one, there's 5, so it's pent. Know your prefixes, so meth, eth, prop, but, pent, hex, hept, oct. It only goes to 8 in the HSC, so oct is where you stop. But it's pretty simple, the prefixes, especially from pent onwards, because those are your standard prefixes for those numbers. But yeah, remember your prefixes. That's step 1 in naming a molecule. Step 2 is deciding its functional group. Here, the functional group is an OH, which is an alcohol. You also see an F in there. That is a halogen. It goes in the prefix. You never put it as like a proper functional group suffix. And then what you need to do is you name it based on the direction. So you need to number them. OH, the C with the OH, that would be 1. And then it would go up to 5. So F is on the 4th carbon. So now we're able to fully name it based on its suffixes and stuff. So it was an alcohol. That means that we're putting ol at the end. There was 5, so it will be pentanol. It will be pent-1-ol because it's on carbon number 1. And then it will have a methyl group on 3 and a fluoro group on 4. Fluoro goes before methyl because it's alphabetical. So 4-fluoro, 3-methyl, pentan, 1-ol. That's how you name them. Main thing to do when naming is to make sure you're getting your order right, so numbering it correctly. You start your number 1 on the side where it's closest to the functional groups, and since the oxygen's on the end, not the oxygen, the alcohol is at the end, that is your carbon 1, where the alcohol is, and then it goes down the chain. And then, yeah, methyl groups, ethyl groups, those are the 2 that you'll probably get, if anything, for your branches. You treat them as a normal, like, branch. As you do with your fluoro, you just put them in there and name them based on the number carbon that they're on. So that's how you do that. If we're going to name this, let's do it quickly now. This one's actually a little bit complicated, but it's fine. We see that there is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's our long chain right there. Then we have a F here and an F here, a Cl here, a methyl group here, and then we have this double bond here. So it is an ene we're looking at. It is a hexene. It's a hex 2-ene. So that's what we're looking at, a hex 2-ene. Then we need to figure out the prefixes. So first we're going to start with our F's. Oh no, we're going to start with our Cl because C comes before F in the alphabet. So Cl, chloride, it is on the 1, 2, 3, 4, 5, fifth carbon, so 5-chloro. Then we have two Fs. One's on 5, one's on 4. So it is 5-chloro, then 4,5-difluoro. Difluoro because there's two. If it was just one, it'd just be fluoro. But since there's two, it's difluoro. So far we have 5-chloro, 4,5-difluoro. And then we need to do the methyl one, which is here. 3-methyl, and then it's hex-2-ene. So overall, it's 5-chloro, 4,5-difluoro, 3-methyl hex-2-ene. So it's a huge one. It's a tough one to name, but got there eventually, so that's all good. So that's how you name that. If we do this practice now, first we find the functional group. This is the functional group here. What functional group is this? If we have a double O with a C and then an OH, that is our carboxylic acid group. Carboxylic acids are always on the end, so that's our number 1 here. 1, 2, 3, 4. 4 is our longest chain length. 1, 2, 3, 4. Yep, 1, 2, 3, 4. Then we have a methyl branch on carbon number 3. So it will be 3-methyl, and then butanoic acid, because anoic acid is, or oic acid is the suffix for your carboxylic acids. So it will be 1, 2, 3 methyl, 1, 2, 3, 4 butanoic acid. So that's how you name stuff. This is just a recap of like how to name things. This is basically everything I kind of just went through, but what you need to do is identify the chain, then do your naming. But the main thing I want to highlight on this slide is this part down here, which is the hierarchy. So when you have multiple functional groups, sometimes you'll be forced to choose one functional group to be the suffix, and then the rest will have to be prefixes. So how you figure out which one is the suffix and which one is the prefix? Let's say there was a carboxylic acid group and also a ketone group. So in the hierarchy, acids are on top. Those alkanoic acids, they are on top, which means they go for the suffix. So yours will be something anoic acid. Then, since there was a ketone, no, let's not make it a ketone. Let's make it an alcohol. So it's an alcohol in the middle somewhere, so a secondary alcohol looking thing, and then an acid on the end. The acid will be your oic acid, that's how you'll name it, and then your prefix would be hydroxy. So that's how you name something with multiple functional groups. You go based on this hierarchy. Hierarchy being top one, carboxylic acids and amines, then aldehydes, ketones, alcohols, amines, then alkynes and enes, then alkanes. How you can remember this is by mass. So the acids are the heaviest are the heaviest functional group, and then the second heaviest are amides. Then it gets lighter for these, and this kind of doesn't make sense because alcohols are heavier than the ketone aldehyde functional group. But basically, what you need to remember is just the order of the hierarchy. There's lots of different ways to remember it. I remembered it by the mass thing and then remembered exceptions, but there's lots of different ways to do it. So everyone has their own way of remembering the hierarchy. You remember your way, and it will help with multiple functional group naming. Naming is something that isn't very common in the HSC, other than when you get to module 8 and you have to like draw up a molecule and then name it and explain how you got it through organic analysis of like the different spectra. That's probably where you'll do most of your naming, but it could also be in a multiple choice question or something like that. So just know your hierarchy, it'll be useful. Next thing we'll talk about is the properties of different series. So main properties that you need to be aware of are melting point, boiling point, and this is increasing as molecules get larger. So as the carbon chain increases, um, or like just in general, the mass increases, melting point and boiling point increase because this increases the number of temporary dipoles, so the dispersion forces. They get stronger and stronger. And this means that it's harder to break those, which means needs more energy, higher melting point, higher boiling point. Another thing here is that solubility decreases as the carbon chain gets longer. This is because the CH2 groups, they are non-polar, they are hydrophobic, which means that they are less soluble. So like dissolves like, polar molecules dissolve polar molecules, non-polar molecules like to dissolve in non-polar. So water is polar. Since water is polar, that means that the non-polar CH2 groups, they are not very happy in water, which is why it becomes less and less soluble. And if we look at the melting point from highest to lowest, this is kind of not timeline, but like ordering. So amides are the highest, then carboxylic acid, alcohol, ketone, aldehyde, and then going down the line. What to remember with these is not only like dispersion forces, but also your whether or not they can form hydrogen bonds and whether or not they have those dipole-dipole forces, and that will determine what has the highest and what has the lowest melting point and boiling point, and that's also how you end up justifying it. So a lot of the questions to do with these properties are to do with justifying like or explaining why something has a high melting point compared to another thing. So that's how you do it. Here are some of the properties of different types of compounds. Alkynes have the lowest melting and boiling point, and they have a high electron density in the triple bond, and they are nonpolar. Then you have your alkenes, reactive again because of the double bond. It says triple bond there, it should be double bond. Not sure why there are so many mistakes in this, but anyway, they commonly undergo addition reactions. Alkenes are also very useful in like polymerization. And yep, C1 to 4 are gaseous. And you also have the nonpolar alkane, insoluble in water, can be involved in substitution. Haloalkanes form dipole-dipole bonds because of the halogens on the end, and they usually undergo substitution with UV light. They're slightly more soluble in water than normal alkanes, and they have a higher melting point and boiling point than normal alkanes because of the ability to form those dipole-dipole bonds. Then you have your amines. They're basic. They can form amides when they react with carboxylic acid. You have your aldehydes and your ketones. They're very similar. The main thing to differentiate them are that aldehydes can be oxidized to form carboxylic acids, and they have a slightly higher boiling point than amines, and then ketones have a slightly higher boiling point than aldehydes. And they have very different smells. That's just a side note. Then you have your alcohols. These have pretty high melting point and boiling points compared to like ketones and also your straight chain alkanes. Alcohols are soluble in water with shorter chain lengths, but as the chain length increases, it becomes more nonpolar, less soluble. Then it can go through a bunch of reactions like dehydration, substitution, and also esterification. With carboxylic acids, it's soluble in water with the shorter chain lengths, just like alcohols are, and they can form esters with alcohol, and they're also acidic because it's a carboxylic acid. Then they have one of the highest melting point and boiling points because they have these two areas for hydrogen bonding, and they have C1 to 4 liquid, C5 and onwards solid. Amides are soluble in water because of the superpolar region, and it decreases with chain length. And then melting point and boiling point is the highest of all the compounds, and that's because it forms really strong hydrogen bonds. So, you just need to know the general trends and properties of those different series and how changing the chain length, changing branching, changing all different types of all different parts of molecules, how that influences its properties. So main things are solubility and then boiling point. So know those. But next part we're going to talk about our reactions. So reactions are the most important part of module 7 because one of the tricky big mark questions that they could give you are reaction pathways, and you can't do those without having a really good understanding of your reactions. So we'll just go through all of the main reactions now. First, we have halogenation, which is an addition reaction, and it opens up a double bond to add two halogens on either side of the double bond. So as you can see there, two chlorides have been added on. Um, and yeah, that's just how halogenation works. Something to note is that if both the alkene and halogen are asymmetrical, then multiple products are possible. When you are writing out the possible answers, you use you draw all possible ones, and then you can often in those questions there'll be another part of the question to help you determine which of the possible products is the real answer. Then you have hydration, which is where you add oxygen, oh not oxygen, alcohol and a hydrogen. And this is another type of addition reaction, but it occurs with water being added. So hydration, I think of adding water. So an alkene reacts with water and it produces an alcohol and it breaks that double bond, and then I think of it as it flipping open. One side gets the OH, one side gets the H, and it requires a catalyst, and this is dilute sulfuric acid. It's just as dilute acid catalyst, but usually it's sulfuric acid. So I just say dilute sulfuric acid. Um, so that's what you do there for hydration. On the opposite end, we have dehydration, which is the opposite. So we start with an alcohol and then it becomes an alkene. It requires concentrated sulfuric acid. So this can be a bit confusing because hydration is dilute, dehydration is concentrated. How I remember that is hydration, you're adding water, and if something's dilute, it has lots of water in it. So that's why it's dilute sulfuric acid there for when you're adding water. Dehydration, you're taking away water. If something's taking away water, it's becoming more concentrated, so it requires concentrated sulfuric acid. And this usually has lots of possible products, as you can see here. The double bond can go on either side, so you can draw both. So you have options, and that's how it works. So the oxygen, it can go this way or this way. You draw both options, and you'll figure it out. Substitution is another one. It's when an alkane reacts with a halogen and it produces a haloalkane. How this works is it requires UV light for the reaction to occur. So that's like the catalyst, I guess. And it swaps. So one of the hydrogens comes out of the alkane and um, swaps with the halogen. So you'll end up with like HCl in this case, when you put one of the Cl's onto the actual chain. Then you have oxidation. Now, oxidation is a cool one. It happens with alcohols and it produces either an aldehyde or ketone or a carboxylic acid. How you can tell what it produces is whether it's a primary, secondary, or tertiary alcohol. So primary alcohols, they produce carboxylic acids. Secondary alcohols, they produce a ketone. And then tertiary alcohols, they cannot be oxidized. So for primary alcohols, the pathway it actually goes through, it goes to primary alcohol to aldehyde, and then aldehyde to a carboxylic acid, because an aldehyde can be oxidized into a carboxylic acid. It doesn't have to start at the primary alcohol, but it goes through that kind of two-step thing, whereas secondary alcohols, they just go from secondary alcohol to ketone and they can't go any further. And for this, you need an oxidizing agent. Two ones that are very common are acidified potassium permanganate or potassium dichromate. That's those two there. And these are the ones that the HSC usually uses in questions. So these are the ones that you'll get used to seeing from practice questions. So Um, Here we can see the different reactions that can occur. And what happens with the oxidation is that we start off with a primary alcohol. We can tell it's primary because the OH is on the end attached to only one carbon. And it goes to form an aldehyde first, and then it forms a carboxylic acid. For the secondary alcohol, where the oxygen is attached to a carbon that's attached to two other carbons, that is secondary alcohol, and that forms a ketone. So the C-double-O bond just goes to the place where the OH used to be. Then with the tertiary one, which is a C connected to three other carbons, that can't be oxidized, so that's why there's no product there. So another type of reaction is esterification, and esterification is really fun, and it is when a carboxylic acid and an alcohol come together to produce an ester. Esters are usually like identified by their fruity smell, and esters are um, they are functional group isomers of carboxylic acids. Um, But basically, what you need for esterification to occur, it's a very specific process. It requires reflux conditions, which means like heat, and in this chamber, very specific apparatus that you'll have to draw. And it requires concentrated sulfuric acid as a catalyst, and usually boiling chips to avoid bumping. But that's not as important as the sulfuric acid and the reflux conditions. And what it forms is an ester and water. So that's how it works. If we look at reaction pathways, this is a common type of question. It can be to identify the different products. It can also be to name the different reactions. So an example question for this would be draw out C, and then what is the reaction that occurs from C to E. So if you were to draw out C, you can look to where it came from. It came from a hydration reaction from B, which was an alkene. And then to figure out whether it's a primary or secondary alcohol, you look at what the next step is. So it is an alcohol that is oxidized. You can tell it's being oxidized because of the acidified permanganate, but it is something that's being oxidized to form C4H9O2. And that O2 tells us it's a carboxylic acid, which means that C is a primary alcohol because primary alcohols are oxidized into carboxylic acids. And that is why we have C4H10O as buten-1-ol. So that's an example of a question you could get with these pathways. Another thing that you could get is just getting you to draw one of these to show different steps to get to a final reaction. For all these reaction pathway questions, main thing that you should be doing is knowing your reactions, because those are the easiest, like that's the way to get to the final answer, by knowing your reactions really well and remembering what requires a catalyst and all that. So for example, at A, it has no reaction when it has no reaction when it's with potassium permanganate, which is an oxidizing agent, which means that it is a tertiary alcohol because tertiary alcohols can't be oxidized. So that's how you should think about reaction pathways. But what we'll do now is go into Module 8, which is all about analysis of chemical compounds. So I did the lecture series in July, so these are the same slides because I did all of Module 8 in that one. So sorry if you were there and you've seen these before. But for cations, main things that you need to do for cations are firstly things like the flame test, and also precipitation reactions. So if you add sulfate, barium and calcium will precipitate, and then you can distinguish whether it's barium or calcium based on the flame test. If you add hydroxide, you can figure out like which ones precipitate, and then the different colors of the precipitates can tell you which one it is. So magnesium hydroxide is white, whereas copper hydroxide is blue-green. Iron 2 hydroxide is white, but it oxidizes to be green, and iron 3 hydroxide is yellow-red. So those different colors can tell you which cation it was initially. Same thing with like if you add chloride to the cations, lead and silver will precipitate, and when lead and silver precipitate, silver will decompose under UV light. So you can figure out which one it is, but based on whether or not it's decomposing. So that's for cations. Main thing with these are just know your solubility rules, so know your precipitates, and then also know your flame test colors. Because for barium and calcium, one goes brick red, one goes apple green. You need to know which one goes brick red and which one goes apple green, just in case that comes up. Then for anions, ways to figure things out are one, add acid because carbonate will produce bubbles. If you add copper, it will form a blue precipitate with phosphate, blue-green with hydroxide, and then the hydroxide can be distinguished based on whether or not it reacts with an acid. Barium will form a white precipitate with sulfate, lead will form white with chloride, and canary yellow with iodide. And that's a really common precipitate to come up because canary yellow, it's a very bright yellow. If you've done a prac before with lead iodide, which you probably shouldn't have because lead is toxic, but if you have, then you'll know how bright the yellow is. It's very bright, and that's a very distinguishable factor, which makes it really good to use in questions because it really shows whether or not you know what you're talking about. But that's ion testing. Main part of module 8, which I think is the most important thing to get down pat, is your spec stuff, your organic analysis. So for organic analysis, it's almost guaranteed that you'll get a question on it in the HSC, which is why I think it is definitely worth getting good at. Basically, your spec stuff, you have your IR spec, your mass spec, and then your NMR. We have HNMR, CNMR. HNMR is a huge pain sometimes, but once you get the hang of it, it's doable. So we'll look at all the different spectrums of ethanol and then do a couple of practice questions. So if we look at this one, we have ethanol and we have 3 different peaks. So it's an HNMR. We have 3 different clusters. Each cluster of peaks represents a unique hydrogen environment. Then, if we remember with the splitting, the number of peaks in each cluster is equal to 1 more than the number of neighboring hydrogens, which means that for this CH3 group here, that CH3 has 1, 2, 3 peaks, which means that it will have 2 neighbors, which checks out because here, 2 hydrogen neighbors. For this OH, it has 1, 2, 3 peaks. Oh no, it's a singlet. It's just drawn badly. It's a singlet. It has no peaks, like no splitting, just 1 peak in its cluster. And that works out because it has no neighbors. It's just the O and the H. This isn't really a neighbor because this here kind of blocks the path. Then for CH2, you have 1, 2, 3, 4 peaks, which means 3 neighbors, and those 3 neighbors are these 3 here. So that's how you read splitting in HNMR. You want to be careful with things like that oxygen, which blocks the way. It's very easy to think that that environment is a neighbor to here, but it's not because of the fact that it's an oxygen, not a carbon it's attached to. So that's just something you need to remember. And then another thing to remember is to ignore the TMS because it doesn't matter. But usually for HNMR specs, you don't get it labeled. You don't get labeled peaks. You just have to figure it out based on how downshifted it is, so how far to the left it is, and also how many splitting peaks there are. So that's that. If we go on to the CNMR spec of this one, it's ethanol, it has 2 carbons, it also has 2 unique carbon environments. One is significantly more chemically shifted than the other, and that's because one carbon is attached to an oxygen, which makes it much more electronegative, which is why it's so much to the left. The other peak is just for the other carbon. It's pretty self-explanatory. Just remember that the number of carbons in the molecule does not mean it has that number of like unique carbon environments in the CNMR, because if something is symmetrical, let's say we have pentane, If you have pentane, you can picture it just 5 straight carbons in a row. That has 5 carbons, but only 3 unique carbon environments because the 2 on the end are the same, then the 2 in the middle, and then the 1 on the very middle. So those are all the same. That's why it's only 1, 2, 3 environments. That makes sense. Then we look at IR spec. So IR spec is the easiest to read because you literally get all the information you need from your data sheet. So if you look at your data sheet, you'll be able to figure out that this here is an alcohol. How you know that is this super broad band around here that correlates to an alcohol, and then this part correlates to the CH. And then this part here, you usually ignore the fingerprint region from here 15,000 and downwards, 15,000, 1,500, 1,500 and downwards. From there on, it's the fingerprint region. You don't really care about that usually, but sometimes there are wavelengths that go into that region that you can see pretty prominently. So that's this, for example. Here, this shows us that there's a CO bond, which checks out because there's a CO bond in ethanol. So that's how you read a IR spec. Main thing is to make sure that you're not getting confused with ones of similar wavelengths. Check how broad it is, and also make sure you're not reading things that aren't really there. So like some people I know would try to read this here. That's just a part of the fingerprint region. It's not something you have to worry about. It does look quite big, but it's not anything you need to worry about. So just read the stuff that goes really close to the x-axis. That's the main rule. If it's touching the x-axis or almost touching the x-axis, if it's dipped down that much, it usually means it's something worth looking into. Then if we look at mass spec, we see that the molar mass is 1, 2, 3, 4, 5, 6, 7, 46, 47-ish. There's a little peak at 47, but that's not really our issue. But it's 46 for ethanol. That's the molar mass. So the little red tiny little peak is something that's probably interference. But we can tell from the furthest to the right peak, the molar mass. And that's really what we need to be getting away from the mass spec in most questions. The molar mass, because it helps you figure out how many carbons there are and then the positioning. So obviously you can read from the other peaks as well to find out how it's fragmented, but usually for mass spec, I only ever use it for finding the molar mass of the molecule because everything else I can find out from the HNMR and the CNMR. So mostly I just use it for the molar mass. But that's how you read those different graphs. Hopefully that was like a quick enough little recap on how to do those. So we will now look at a question. This one only has 2. It gives us the CNMR and it gives us the IR spec plus a formula. So that tells us what the mass spec would have told us. We don't have HNMR, which probably would have been useful, but that's okay. So we have C3H6O. This tells us that it could be multiple things, but if we look at the IR spec, we can look at the little peaks, the little downward sections, and from this you can tell that it is, well, if you look at your data sheet, you'll be able to tell that it is a C-double-O bond somewhere. And the real question is, where is the C-double-O bond? So that's what we need to figure out next. Where is the C-double-O bond? You look at the CNMR, there are 2 carbon environments only. 2 carbon environments. 2 unique carbon environments with 3 carbons. That means there's only one option, and that is this. So here we can see the 2 unique carbon environments, this one, these 2, and then this one here. And this one is the most downshifted one because it's attached to that oxygen. Then these peaks are correlating with the C-double-O bond. You can also tell that it was an alcohol, an aldehyde or a ketone based on the formula alone. You didn't really need this, but you still could use it, I guess. But that's kind of how you go about it. Since there were only two unique carbon environments and three carbons, that's how I was able to tell that there had to be that symmetry, and that's the only way it would be symmetrical is if this was in the middle. So that's how you work it out. For a question like this, we have all four going on here, and that means there's quite a bit of work to be done. But what we need to do is we need to look at the different parts of it. So first thing to do, we look at the IR spec, and you'll see what what is it? What is the what do you call it? What is the functional group? So main peak is this one here, around 1, 2, 3, 4, 5, 6. So 1,700. It's around 1,700. And you ask yourself, what does that correlate to? So you look at your data sheet, figure that out, keep that in mind. Then, next thing you need to do is you need to look at your mass spec. So this one doesn't have a formula. We weren't given a formula. So what we have to do instead is we need to figure it out based on this. So it's around, I'd say 87 as your molar mass. So 87, and this, it's a C-double-O bond. And that here is super broad. That means it's a carboxylic acid probably. So that's a carboxylic acid. This is your C-double-O bond. That checks out because there's a C-double-O bond in a carboxylic acid. Then the next thing you need to do is figure out how many carbons would have to go in a carboxylic acid for it to be 87-ish, 87, 88. We'll go with 87. 87 molar mass, and you'll see that that requires 1, 2, 3, 4 carbons. So you have 4 carbons, and you'll realize that butanoic acid does not work. Butanoic acid would not work because butanoic acid would have 4 unique carbon environments, and this one only has 3. So what you do then is you have to consider symmetry, and you need to consider a methyl branch happening. So that's how we get something that looks like this. So we'll check it with the carbon environments. So 1, 2, 3 carbon environments. We have carbon environment 1, which is here, then carbon environment 2, which is here, and carbon environment 3, which are these two, which are the exact same. 1, 2, 3. Yep. Then if we look at the unique hydrogen environments, we have 3 clusters of peaks. We have one that is super downshifted, which will be this hydrogen here, and that's a singlet. So it doesn't have any neighbors, which checks out because it has no neighbors. Then you have this one in here, which has lots and lots of peaks. There should be 7 there, and that corresponds to this hydrogen environment here, which has 6 neighbors. Then this one here is a doublet. It has 2 peaks. Those 2 peaks means 1 neighbor, and that neighbor is this neighbor. So that's how you go about working that out. And that is that. So basically, the main things that you need to keep in mind for Module 8 in general, especially for these, is first of all, the broad stuff. So this, it's not going too close to the x-axis, but it is super broad, and your carboxylic acids are always going to be really broad. So you want to remember that. Then you also want to ignore the fingerprint region, focus on stuff like this. For mass spec, sometimes there's a little like peak after what is a prominent peak for molar mass. That can be a bit confusing sometimes, but just know that it's the first, like, it's the furthest to the right peak that's actually like a peak, not a little like a little dot, I guess. Then my tip always is the CNMR tells you a lot about symmetry. So if there are less carbon environments, unique carbon environments, than there are carbons in a molecule, that means that there has to be some sort of symmetry. And the first thing you should always do is chuck on a methyl branch somewhere. Chuck on a methyl branch, and that will make it a big difference in the amount of carbon environments you have. And usually with the splitting, symmetry is something that can make people very confused, because like the carbon environments don't line up and the hydrogens don't line up. So you need to be really careful with your branching and making your molecule like symmetrical if it needs to be for like decreasing the amount of carbon environments there are. And then for splitting, splitting can be a little bit tough, but that's okay. Splitting, the main thing to remember is splitting is that the number of peaks is one more than the number of neighbors. It's one more than the number of neighbors. And you need to remember what constitutes being a neighbor or not. So just like it was before with the with ethanol, this hydrogen doesn't have a neighbor. It looks like it could be a neighbor with this hydrogen here because it's connected to the C and the C is connected to here. It could be a neighbor. It's not a neighbor. It's too far away. If it were here, like I know it can't work because of the bonding, but if there was an H here, that would be a neighbor because it's connected to that C there. But this H is connected to an O. It's connected to an O, which is then connected to the C, which means that the neighbor is here, not a neighbor. It's not a neighbor here. It wants to be, but it's not. Other things to know are if you're given, like in this question here, this question where it's C3H6O, a really good way to start like speeding up the process of answering the question is by trying to figure out what functional group it is based on the formula. So from the formula, you know it's not an alcohol because if it was an alcohol, it'd have an H. It'd be like C3H7O or C3H6OH. It's got the wrong amount of hydrogen. So you know it's a C double O bond. You just don't know where it's positioned. So you can completely bypass the IR spec to do like just looking at the carbon environments from there, and it'll make it much quicker. Um, if you look at like the HNMR for this molecule here, you'll see that there's only one unique hydrogen environment and it has no neighbors. It'll just be a singlet, and it will just have a bigger relative peak area because there's 6 hydrogens in there. But you can try to skip over as much as possible and by like looking at the formula and thinking about the different isomers for that functional group or for that formula. So if you get something that has 2 oxygens, you know immediately that it's going to be either a carboxylic acid or an ester. Then you can just skip straight to drawing those options out or looking at the IR spec and then seeing if it has that really broad band. That's a part of a carboxylic acid, or if it has that CO bond, that's like an ester. So you can find these little shortcuts to make these kinds of questions easier. But the main way to make these questions easier for Module 8 is to practice. So if we look at this one here, an even more practice one, this one we can tell a lot from the what's it called? The IR spec. IR spec there, you can see the broadband that relates to being an alcohol, and then you have the less broad one, the little one, that's just a CH bond. So we know it's an alcohol of sorts. Then if we look at the C NMR, we have two, two carbon environments, 2 unique carbon environments. And then for hydrogens, we have one that has lots and lots of splitting, and then one that has a little less splitting. So what my tip would be, since we're looking at this HNMR on the side here at the bottom, you see that there's a lot of splitting, and naturally, like the splitting doesn't come normally looking like that. As in, usually a carbon only has like 3 hydrogens. You don't usually get more than 4 peaks in a cluster unless there is some sort of symmetry happening. And that, like lots of peaks, is an indication that there is a methyl branch somewhere or an ethyl branch. There is a branch somewhere where it's not just a straight chain, it's got a little side area. So with looking at that, you are immediately able to tell a little bit about how it is structured. Um, so the next thing you would have to do is draw out your options, and then you will figure something out. I will not tell you the answer for this one. I will leave it for you guys to practice at home sometime, I guess. Um, but yeah, I think that these questions are almost a guaranteed in the HSC, so it's something that you should definitely get good at. Um, and it's actually not that hard. It looks really hard at the beginning, but it actually is not that difficult once you get used to them and once you expose yourself to a bunch of questions. Another thing I will say that there's not a practice question in this slide deck for it, but one time in my trial for chemistry, they gave me one of these module 8 questions where it included a halogen. It included like a chloride somewhere or a bromide in the chain, and it told us that, but it had to we had to kind of figure out where it was positioned, and it was really tricky that way. So just keep in mind that they can throw you curveballs like that. They can add in a random, yeah, they can just add in a random halogen into the mix, and that can really throw off your splitting because it's no longer like the neighbor might not necessarily be a hydrogen, so that's not getting picked up. So you just got to be really careful with things like that. So if you get a mass spec and the molar mass is huge, it's like in the hundreds, and like you know from the IR spec that it's like an alcohol or something, like it's not a really heavy functional group, just consider that they might have thrown in a halogen in there. Usually they'll tell you, but I don't know how mean they're going to be to you guys this year. So like just know that that's something they can do. They can add a halogen in randomly to your like organic molecule and then make you do it. But yeah, that's that. Um, so we are going to do a quick little summary, I guess. Um, it's some unsolicited HSC advice more than a summary. But in terms of like an actual summary of what we did today, my main advice in terms of like proper chemistry stuff to take away is just like do practice questions. I think that practice questions are the most useful way to study because the HSC are questions. You're not doing like blurting, you're not doing flashcards in the HSC, you're doing questions. So practice questions is something that are the best way to mimic what you're actually going to do in the HSC. And I'd say try to do full length papers because how papers are set out with the multiple choice and then the short answer questions, past papers have a good balance of short answer, calculation, and long response questions. So you don't want to just be exercising your calculation questions and then thinking you'll be fine for doing long response questions without ever having practiced those. So take take a full practice paper, like do a full practice paper, and it will help you figure out what areas you're good at, what you're bad at, not bad at, what you are still getting good at. And you'll figure out what to focus on from there. But in terms of HSC advice, congratulations on graduating and on getting to the actual HSC, which is the scariest part. I think the scariest part about the HSC is if you think really hard about it, it's worth 50%. So all your internals, all your trials and stuff, they were worth so little compared to the actual exam. So it can be a bit stressful, and like understandably so. I was very stressed, but there are lots of things that you should remember during these times that are like not academic based that I still think are very important because the HSC can feel like a life ruiner. It can feel horrible and sad and just not a fun time, but it doesn't have to be that way. Um, I know like a lot of the stress is on like getting a good enough ATAR to get into the uni you want or just like passing it or just getting by. Everyone has these different goals. So just remember your goals and remember why you were working towards that goal and it will kind of put things into perspective. So for me, I wanted as high of an ATAR as I could possibly get. I wasn't expecting a 99.3 by any means. I was just wanting to get the best I could possibly get so I could have as many options as I had. Um, yeah, because I was a little bit confused with what I wanted to do. So I wanted to give myself as much room to work with as possible. So that was my goal, to do my very best, and I did that. And I definitely say, I said this at the beginning, but trust your preparation. So I think coming to a lecture like this is a really good start because it shows that you're dedicated enough to seek help on chemistry and revise chemistry and take time to actually do chemistry. So um, they're like, trust your preparation. You're already doing really well by coming to something like this. And like um, I did put on the slides like a bunch of practice questions you can do once this lecture is over and once you have access to the slides. So like do those practice questions and that will help your preparation even more. Another thing you can definitely do is time your exams and do them like in a 3 hour block. Sitting still for 3 hours sounds really scary and really tiring, but it'll be fine. Like you got it. It goes by really fast when you're stressed. And then I said this at the beginning, but I will say it again because I think there's nothing more important. And it's that the HSC is never, ever, ever more important than your health. So stay healthy, drink water, go to sleep, do fun things, go outside, go for a walk, do some exercise. Just try your very best to balance out your life. Um, I say that, and I didn't really do that very well in the HSC. My life kind of did stop. But I still definitely made time to have like dinner with my family. I didn't like hold myself in my room as like a hostage until I finished studying. I just tried very hard to stay social and met my friends at the library, spent a lot of time like, I don't know, gossiping in the library, but also doing work. It's just try to stay friends with people and try to think of everyone as teammates rather than competition. Um, that's a really big tip actually that I didn't write on this slide, but it's really a team effort, the HSC. The better your cohort does, the better you do, especially because of rankings and things like that. So try help each other. Don't go gatekeeping your resources and gatekeeping your methods of study. Try to help everyone because everyone can use a little help during this time. And try your best. Your best is definitely good enough, and you will get the result you want. You've worked really hard, you deserve it. Don't doubt yourself for a second. And also be proud of yourself because the HSC is the end. And look how far you've come since the start of the HSC year. It's been tough. And you've already done like a trial, which is 3 hours long, already gotten through that. So if you can get through that, you can get through the HSC. I am serious when I say the trial is harder than the HSC, just because the trial is the first time you're ever doing something of that length and of that kind of style, whereas the HSC, you've done it before. Not the actual HSC paper, but you've done an exam like that before, so it's not as scary. So, although you've already like although it's kind of scary, you've already been through some tough stuff. So, um, the year is almost over. You've been through some really hard stuff already. So, what's one more exam? That's the way I thought about it. I was counting down the days until I finished my HSC. So, just know that it's almost over. If you're stressed and nothing is making you happy about the HSC life, just know it's almost over. And then get excited because life doesn't stop after the HSC. Whether or not you choose to go to uni or travel or gap year, go straight into working, do an apprenticeship. There are so many things that you can do after high school. So like get excited because you might have a plan, you might not have a plan, but even if you don't have a plan, there's still lots of cool stuff to look forward to. You could come to UCID, you can come see me on campus, you can do lots and lots of stuff. So um there's lots of stuff to look forward to. Um, like my key tip for what I said last lecture was that like give yourself something to look forward to after, like I don't know, set a date to have a picnic with your friends or go out somewhere fun, like axe throwing to stop your like aggression and your post HSC stress relieving stuff. Go axe throwing. That's kind of fun. But yeah, just there's lots to look forward to. So, um, there's that. But that brings me to the end of the lecture. I hope you learned something today. Even if you didn't learn something, I hope you were like somewhat entertained by this 2 hour thing. Hopefully, it wasn't a waste of time. But good luck for the HSC. You'll all do very well, I'm sure of it. And if you had any questions, hopefully someone's been answering them in the live chat. I'm sorry I couldn't be there to answer the questions. You guys will be done by then, but like next year I'll be answering the questions hopefully on the live chat again. But thanks for coming and good luck. All the best. Maybe I will see you at Sydney Uni, who knows? But yeah, have fun. Don't stress too much. You've already done a great job. And yeah, just overall, good luck for the HSC. You've got it. Thanks for coming. Bye.